Prevalent manifestation of grouping behavior of many species and is cooperative hunting, which is observed across various species including lions, African white dogs, chimpanzees, wolves, and birds, etc. In prey-to-prey interaction, the sensitivity of prey population to prey dogs plays a crucial role in regulating the system dynamics. So, in this study, our primary objective are the following inquiries. First, what are the dynamical repercussions of fear-induced modification and hunting cooperation within the context of a modified residual models, and to what degree does the predator sensitivity influences our proposed model, and how the seasonality in different ecological factors impact the dynamics of our proposed system. So now we construct our mathematical model. So let xt and yt be the densities of prey and predator population within an homogeneous environment at time t greater than 0. Then the Leslie-Gore model with volume type to functional response can be represented as this figure where lambda 1 equal to 0.1. We observe that the system exhibits unique interior equilibrium point, and for lambda 1 equal to 0.7, system exhibits two interior equilibrium point, and when lambda 1 is high, that is lambda 1 equal to 2, there exists no interior equilibrium point. So we perform local stability for this equilibrium point, and we find some condition under which this equilibrium points become stable or unstable. So we graphically illustrate the behavior of this equilibrium point, and for this plot solution trajectories, and when we choose this initial condition from near this population equilibrium point, the solution trajectory goes to this star, and when we choose here, the solution trajectory first goes to E1, and from there it converges to star. So from this figure we observe that the interior equilibrium point is stable, and these two population, that is axial equilibrium point, peripheral predator field, is has saddle behavior, and population field is unstable. So we perform transcritical bifurcation, find some condition under which our system undergoes transcritical bifurcation. Also we observe when our system undergoes Hopf bifurcation. Now we perform semi-relative sensitivity analysis. So the semi-relative sensitivity analysis quantify the changes in prey and predator population when the values of a specific parameter is doubled. So first we double the value of a parameter, and we see how the population dynamics changes. So from this figure we can conclude that when we doubling the values of parameter R0 and alpha, the predator density increases, and when we double the parameter values K1, K2, and lambda 1k exhibits decline, whereas the lambda 1k exhibits an incline in the predator density. And from this figure we see green line and blue line is the nearest line to the zero line. So from this we can conclude the parameter alpha and k1 are the least sensitive to the changes of the population. So we perform logarithmic sensitivity. Here we perform different dynamical exhibited our proposed system. So when R0 is very less, there exists no interior equilibrium point, and only prey equilibrium point exists, and in this region bistability occurs between interior and prey equilibrium point, and when R0 is greater than 1.7, so there exists prey equilibrium point which becomes unstable, and one coexistence equilibrium point disappears. So from this investigation we can conclude that for lower values of prey birth rate, there exists no prey population within the system. However, the predator population can persist within the system. So we show this by bistability behavior by phase portrait, and we perform some bifurcation with respect to some parameters to show how the dynamics changes when we vary these parameter values. So we show existence of saddle node bifurcation, and we perform two parametric bifurcation diagram. So here we draw the transcritical curve and Hopf curve, which divides the plane R0, K1 and the others into different regions with unique dynamics. So each regions are described here. And now we introduce seasonality in some crucial model parameters, and we observe that when we introduce seasonality in our model parameter, the system exhibits periodic, high periodic bursting patterns, and many more. And we also, and now our conclusion of our investigation. Predator taxi sensitivity was revealed to exert both stabilizing and destabilizing effect on the predator prey system, and similar impact observed for this parameter also ultimately lambda, and notably fear parameter, that is A1 and A2, emerges as the crucial determinants active to reduce instability and promote the system to stability. And lower prey growth, higher predation rates, and the increased cooperative hunting can lead to the extinction of prey population, and higher prey growth, lower predation rates, and diminished cooperative hunting may facilitate the coexistence of prey and predator population. And the predator taxi sensitivity demonstrates the capacity to influence the densities of prey and predator population, and seasonal influence in the model in the predator taxi sensitivity resulting in the extinction of prey population. The cooperative hunting and predator taxi sensitivity exert prohibited control. The insights derived from this investigation hold substantial biological importance. That's